This is our final lesson for our Waves and Quantum Mechanics unit for Physics 11. And what we're going to do today is just see the very, very beginning of quantum mechanics, the first kind of experiments that physicists looked at and said, hey, wait a minute, something's different here. And then they had to develop the whole world of quantum mechanics after this. And specifically today, we're going to look at something called the photoelectric effect. So I'm just going to kind of tell you basically the story of where the quantum mechanics begins. And we're going to go all the way back to when physicists were thinking about the colors of the rainbow. This is, they knew about this well before quantum mechanics. The rainbow with its Roy G. Biv colors represents all the colors that we as humans can see with our eyes. And this is just light that's arriving at our eyes with various wavelengths and frequencies. But that light's going to arrive, if it's through air, at the speed of light 3 times 10 to the 8 meters per second. Now, just kind of tearing the rainbow apart a little bit, we like to remember it as Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. Some things that you need to know just to be kind of ready to recognize quantum mechanics when it shows up is the frequency and the wavelength for the various colors. So I'm just going to offer you a few numbers here for either end of the rainbow. For the red end of the rainbow, physicists were aware of this for a long time before quantum mechanics, that the frequency is around 3.7 times 10 to the 14 hertz, and that the wavelength for that light is 800 nanometers, 800 times 10 to the negative 9 meters. We really like using the metric system when we talk about these small wavelengths. It's just a lot easier to say 800 nanometers than it is to say 800 times 10 to the negative 9. Or even 8 times 10 to the negative 7. That nanometers is just an easier way to say it. Up at the bluey purple end, you're going to find that the frequency is roughly doubled, 7.5 times 10 to the 14 hertz, and the wavelength, just roughly speaking, just aggressively rounding here, is around 400 nanometers, 400 times 10 to the negative 9 meters. So it's a key takeaway here before we dive into the quantum mechanics is that blue light, bluey purple light, has a higher frequency than red light. That's going to be an important issue in just a moment. Now, the next issue that we need to talk about is something called black body radiation. And this is just what happens if you take something like a black piece of metal and heat it up, like a stove element, or just a briquette in a barbecue. When you get it hot enough, it actually starts glowing and giving off light. And that light that it gives off is called black body radiation. So I'm just going to put in the notes here, if you heat up objects, especially dark colored ones, like a dark piece of metal, that just works better for us. They will glow and give off some nice light to them. But here's what's interesting. The colors that they give off are not quite right. If all you go by is the idea that light is a wave, and we have the Rutherford model of an atom with electrons flying around the outside, you can actually do some reasonable math and show that when you start heating materials up, like a stove element, and get them hot enough, and if you start looking at how much of each color of the rainbow light comes off, you should find that you get less red light off than green, and less green light off than blue. And you should have more blue light than any other light when you start heating up some materials. But what you find if you take a look using like a diffraction grating to break up the colors, what you find is in real life, the actual curve kind of follows that for a while, and then all of a sudden it drops off like a cliff, and the higher colors are not there. And so physicists were looking at this and they're like, okay, well, we have something wrong. One of these two assumptions for our math isn't quite right, that light's a wave or just the Rutherford model of the atom is going to be fine. We need to refine our knowledge of physics and come up with a better model that can actually predict this curve. Another interesting thing they noticed about this actual curve of light intensity, this spot where it drops off, I've got it dropping off way up here in the blues, it actually drops off at different spots depending on how hot the material is. So if the material is fairly cool, like maybe a stove element just starting to glow, you might find that that cliff is fairly early, around the reds and oranges. But if you get things quite hot, like the temperature of a nice blue star, then you'll find that that little cliff, so to speak, is actually pushed farther along. And you can tell actually how hot an object is just based on its color, right? So when stove elements first start to glow, it's a very deep red, and then you kind of get oranges, and then kind of an orangey yellow, and then maybe a bright yellow if you're in a foundry. And you get up to the temperature of some very hot stars, and you'll actually notice that unlike cooler stars, which are red, they're actually very blue, right? So a blue star is much hotter than a red star. Okay, the next person who comes on scene actually comes up with some math that matches the curve that people were noticing, this actual curve. And he's playing around, his name's Max Planck, and he says, whoa, wait a minute, I've come up with something that actually gives you the right curve. And people are looking at his work and they're like, okay, well, what have you found? What did you do? And he said, well, here's what I had to do in order to get the curve right. But I've definitely come up with something that's predicting the correct black body curve. He said that light arrives not as a nice, smooth, continuous wave, but it seems to arrive in little packages. And each one of the packages always has the same amount of energy for a given color. So red packages have one amount of energy. Orange packages, they all have a slightly different energy. It's a little bit more. Green packages, they all have a little bit more energy. Working your way all the way up to the blue packages, which have the most energy. And this idea that light was packaged is just unheard of, right? And people were like, what? There's no way it's like that. It's a wave. It's nice and smooth and continuous. It's kind of like if you go to a restaurant and you're going to get some French fries and you're looking for some ketchup. You know, maybe they've got one of those dispensers where you can just kind of just pour out exactly the amount of ketchup you want. That was the old theory with the waves. You know, how much energy do you want? But the new theory, it's kind of like you're going through the drive-thru and you're talking to the person at the drive-thru, and if you're asking for some ketchup, they might say, well, how many packages of ketchup do you want? And you have to take whole packages. You can't take, in a drive-thru, 2 1/4 packages of ketchup. You can have 2 packages or you can have 3, but you have to take them in complete packages. And so a lot of people were very skeptical of this when they first heard it, but he's like, look, it matches the curve perfectly. And so when you have this idea that something comes in packages, we say it's quantized, right? And that's where we get the name quantum mechanics, right? It's all about packaged mechanics. And Planck is saying, I think that light doesn't arrive as a nice smooth wave with any amount of energy you want, but it comes in these little quantized packages. And the amount of energy in each one of these quantums, each one of these packages, is given by this equation. So E is going to stand for the energy in that quantum of light, and F is going to be the frequency of the light, and then there's a constant just to get everything to work, and that's Planck's constant. And it's on your formula sheet. It's just a number that you can look up. And once you know what color of light you want to play with, you look up its frequency. You can multiply that by Planck's constant, and you can see how much energy is on board each quantum. Now remember, I'm going to go back in the notes here. Just back. Back here we said, oh, blues have higher frequencies than red. So if blues have a bigger value for F, for frequency, then what we're going to find is if there's a bigger value in here for F, we're going to get a bigger value for E. And so here's a little legend of what all of the items are. Okay, so E is the energy in joules. It's going to be very small for a package of light. F will be the frequency in hertz, and then H is Planck's constant. And again, that's just a number you can look up. Don't worry too much about the units. That's just the quickest, cleanest way that the physicist can write the units down. Let's try this out for a little package of blue light, which remember, does have a better frequency than red light packages. So for blue light, the frequency is around 7.5 times 10 to the 14 hertz. Roughly double the energy that you would have for a red package. And what you find is every single package of blue light has this very tiny amount of energy, 5 times 10 to the negative 19 joules. It is small, but if it was red light, it would even be smaller again. It would only be half as big. And so a lot of people are looking at this and they're like, are you sure? Like, I don't know. It doesn't seem right. Light's definitely got to be this nice continuous wave. And he's like, well, it does actually match the experimental curve that we're seeing. And it's all about this idea that light comes in packages, and then blue packages would have more energy than red ones. And that's why we don't see so much blue light on the curve than we do reds. The packages are harder to create as you start to heat things up. Well, there were some skeptics, but the next person who comes on scene is Albert Einstein. And he says, Planck, I think you're right. And I got a little experiment we can do to actually prove it. And so this is called the photoelectric effect. It's actually what Albert Einstein wins the Nobel Prize for. and it is remarkably simple in terms of how you can draw it out. We're going to have a battery that's going to try to get some current to flow. We're going to have a very sensitive ammeter, and I've got a little glass tube here with some little metal plates on the end. Now, I know Benjamin Franklin would say the electric current's coming out of the positive end, but in actuality, we have electrons coming out of the negative end, going clockwise in this picture on my blue wire. And you can see them all piling up here, and they can't seem to cross this river. So what we're going to do is try to kick them off that plate. If we can just nudge them off the plate, they will not want to hang around here. Can you imagine being an electron if you got just bumped off this plate like you're right there? You're not going to want to stay there with all these other negatives around. You're going to want to move over to here, land on the plate, go through the ammeter, which will record some electricity, and then we'll just keep playing the game. And we just have to shine some light on that plate in order to knock those electrons free. So Einstein, he's buying into Planck's idea that light is going to arrive in little packages, right? These little packages of light are going to come in and then try to knock those electrons free. Okay, so the old theory, the old school way of looking at it, is that no, light's just a wave, and it doesn't really matter what color you can use. For that matter, why don't you go ahead and use red and shine some red light on that plate? And they try it, it doesn't work. And so the old school way of looking at it says, well, your light's not bright enough. Shine a brighter red light on that plate. No matter how bright you try to shine it, it just doesn't work. But Einstein knows this, right? Because he knows that it's just an issue of package size. And the red packages, as they arrive and land and try to liberate those electrons, they don't have enough energy to do it. They're just too small. So Einstein says, all right, new way to look at it. Light is quantized, comes in little packages. And now is when we're going to give them the name. We're going to call them photons. So a photon is the tiniest package of light that you can imagine. So we're going to have these photons arriving, and depending on what color light bulb we use, they're going to have different amounts of energy. If you try it with a red light, well, the red photons just never have enough energy to kick those electrons free from the metal. Maybe when you get down the rainbow a little bit, maybe you'll find a color like maybe around green, where it's like, okay, now there's just enough to knock it free. And they're being barely knocked free and then making their way along, and the ammeter shows some current. If you can use a color more energetic than that, like blue, well, not only will you knock them free, but you'll even give them some kinetic energy along the way. So they'll come flying out of there. And we try it out. Well, not me, but Planck and Einstein, they try it out, and it works perfectly. And so this proves that light is actually quantized, that it actually comes in little packages called photons. Now, what's interesting is the very last lesson we did, we talked about light being a wave and doing interference. It can do both, right? It's this wave-particle duality of light. Depending on what experiment you're doing and what size of thing you're kind of measuring, you might see it behave like a wave, or you might see it behave like a particle. And in this experiment, it is definitely a particle. Waves just don't do that. There is a little equation that we can use, and it's what we're going to finish up with. In fact, let's go over the page and we'll see how this works a little bit better. So this is called the photoelectric effect equation, and I want you to think of it just as conservation of energy. That's all it is, right? It's just some conservation of energy for that incoming photon giving up its energy to try to knock the electron free. The only challenging thing about this equation, the two sides talk about completely different things. On the left-hand side, this is going to be a photon coming in. You can see that Planck energy there, right, HF? And that photon is going to give up its existence when it strikes the metal. And it will donate all of its energy, its existence, so to speak, to an electron to try to knock it free. Well, there is a price to try to get an electron out of that metal. It's tough. It's not an easy thing to do. It's going to require some work. And that's what this W is. Different people use different letters here. I'm going to go with W for work function, to try to push that electron out. And if you have extra energy from your photon, maybe it's a nice blue one, not only will you work it out, but you might even be able to give it a little kick, a little kinetic energy to go along its way. And so here are three different calculations you might see based on three different colors trying to knock an electron free. Well, let's come up with a work number for how much it does take to knock an electron out of this metal that we're talking about. It's called the work function, and it's just the energy required to free the electron. Every element has its own work function. So sodium has its own work function, aluminum has a work function. I'm going to just go with a make-believe number, 4.0 times 10 to the negative 19 joules. That is the minimum amount of energy it's going to take to be successful knocking an electron free from some metal. So let's try out some red light with some red photons. So I went and looked up frequency for red, 3.8 times 10 to the 14 hertz. We're going to throw some little red packages at this metal. When I do the calculation for HF, when I multiply it by Planck's constant, that 6.6, 10 to the negative, whatever it was back there, no, forgotten. I have to go look here. 6.6 times 10 to the negative 34. I couldn't remember if it was 34 or 36. 34. When I tried that out, I ended up with 2.5 times 10 to the negative 19 joules. That number is not enough. That is not enough energy to knock even a single electron free. And so the electron will take that energy and say, thanks, but I'm not going to leave. And then it just kind of wasted away and just in some heat, wiggling. And so what you find is nothing occurs. There's no electric current. The electron stays put in the metal, and it's because your energy is just too small. Well, somewhere out there, and I tried to get it to 3 sig figs, somewhere out there is just the right color with just the right frequency to have just the right energy. And so around green, around 6.0, 10 to the 14 hertz, that particular color has just the right energy for its packets that it will actually knock it free. So you will now see an electron given off, but at this point, for this story, because you just made it out, because this number is equal to that number, there wouldn't be any kinetic energy. It just kind of falls off the metal, right? It wouldn't go running away, so to speak. But it would definitely start to work. We're going to start to see a little bit of current because that electron will be freed. What if we go a little higher? Let's go to an even bigger frequency. Now this time I'm going to make us work for it here a little bit. What if I go with a wavelength, not giving you the frequency just yet, of 410 nanometers? Well, if they do that to you, if they give you wavelength instead of frequency, it's a little less convenient. Not a problem. We'll just use the wave equation, and we'll use a velocity of 3 times 10 to the 8 meters per second. Kind of ironic, though, that we're using a wave equation to talk about how light's a particle, but that's okay. Turns out you can do this. So putting in the speed of light, putting in 410 times 10 to the negative 9 for my wavelength, I can just go and calculate the frequency, and it ends up being 7.32 times 10 to the 14 hertz. So it's definitely not the end of the world if people throw you a wavelength instead of a frequency. Now we can keep on going and find out what our HF value is. Check it out now. 4 10 to the negative 19 was just enough to knock the electron free. We now have more than that, right? 0.85 times 10 to the negative 19, or what probably people would call 8.5, 10 to the negative 20. We're going to have a little bit of extra energy, and that's all this photoelectric effect equation is about. It says, all right, well, you've got this much energy here. It's going to take that much to get it free. Hey, you're going to have a little bit left over, right? This is awesome. And so we can subtract to see exactly how much we're going to have left over. So there I am operating the photoelectric effect equation to find out how much kinetic energy is available. And what I found is that this electron is going to get launched out of there. It's going to have some EK. And I can just go and look up the mass of an electron on my formula sheet and see exactly what kind of speed it could leave at. So here is my 0.85 times 10 to the negative 19, just a different way to write it. 8.5, 10 to the negative 20, 1/2 mass of an electron, and then speed squared. Sloshing that around, it ends up leaving there pretty quick. 4.3 times 10 to the 400,000 meters per second. It's going to get launched out of there. And even a little bit of blue light makes this work, but tons of red light doesn't. And that verifies that light can actually behave as a particle. And that's the end of our chapter. It's just the very first peek into quantum mechanics. At least you can see where the word comes from. That in this story in physics, stuff is quantized, comes in little packages, and turns out the energy from light does that, just depending on the color. And with that, we're done.